Hi folks, welcome to the second video in your 10.4 lecture series. And in this video, we're going to take a look at the shortcuts that we can find when we're looking for the error in the approximation for alternating series, okay? So the key here is that we're going to be looking at alternating series, which was not the case in example number 1 that we did. So I'll just make a note for us here that we're looking at alternating series for example 2 and 3. Okay, so let's take a look. Example 2 says, evaluating the Taylor series at 0 for f of x equals 1 plus x at x equals 0.3 produces the following series. And you can see that they're actually just giving us the series, okay? So 0.3, 0.045, 0.009, etc., etc. And I can see that the first term is positive, the second one is negative, then positive, then negative, then positive, then negative. And so that's what I'm looking at when I'm saying, oh, is this an alternating series and can I use that? So it says use two terms in this series to approximate natural log of 1.3. Then estimate the error in the approximation. Okay, so for our approximation, right? So what we're going to do is we are going to use two terms, okay, to approximate. So in other words, ln of 1.3 equals 0.3 minus 0.45. Like, that's what they give us, okay? Now, when I take these two numbers and I go ahead and I subtract them, oh, that's the wrong number, 0.45. Let's see what we get. So 0.3 minus 0.045 gives me 0.255. And this is my estimation. Okay, this is my estimation. Now, we know from our previous video that if we want to find our error, that we can go back to our equation that our 2 of x equals f of x minus p2 of x, okay? And last time we rearranged this, we said that f of x was really going to be p2 of x plus r2 of x, right? So we did some algebra, we added the p2 to the same size as the r2, and that's another way that we can say find that estimation plus the error, okay? So when we're using the first two terms, our p2, we're approximating 0.3, plus our r2 term. So this is going to be the third derivative, right? Because 2 plus 1 gives me 3 of 0.3 cubed over 3 factorial. So this should actually look pretty similar to what we had in the last one, last video, because we're also looking for that second degree polynomial, okay? So let's do some substitution. We know that our P2 of 0.3 was 0.255 from above, okay? So this is our estimate plus whatever we get over here is going to be our error. Like, how far are we from what we actually want, okay? So I'm going to do a little bit of work off to the side here. So let's leave ourselves a little trail. But what I have to do is, like, I know I can do 0.3 to the third on a calculator, and I can do 3 factorial on a calculator, but what I need to find is the third derivative of the function that I'm looking at. So I know my function is the natural log of 1 plus t, or 1 plus x, excuse me. right? And so we've got natural log of 1 plus x. Now I have to find the first derivative, the second derivative, and the third derivative, okay? So the first derivative, I'm going to get 1 over 1 plus x times the derivative of the inside function, which is 1. Okay, so we got to use our chain rule here. But it might be nicer if we write it as 1 plus x to the negative 1, because that way I can prepare myself to use the power rule for my further derivatives. So my second derivative is going to be negative 1 plus x to the negative 2 times 1, again, for my chain rule. And my third derivative is going to be negative 1 times negative 2, 1 plus x to the negative 3 times 1. Now this, let's go ahead and clean up because this is the one we're going to use in our equation. So negative 1 times negative 2 is 2, and then 1 plus x to the negative 3 is the same as 1 plus x to the third in the denominator, okay? This is what we're going to use for our f3 of t. So I've got 2 over 1 plus t to the third times 0.3 to the third over 3 factorial. Okay, now the only thing left is to pick a value for t. And if you remember last time, remember t has to be between 0 and whatever x number we have. And in this case, the x number is 0.3. So I know from here that t has to be between 0 and 0.3. And all I have to do is get a graph of my not of that one, get a graph of my derivative and see where that highest value is. Where's the highest y value? Okay, so if we use our Desmos, we should see a graph that kind of looks like this. Almost. Okay. And if we're looking between 0 and 0.3 in for our x, we can see that the 0 value is higher. So what that means is I'm going to plug in 0 for my t, okay? So this will be my error term. We've got 2 over 1 plus 0 cubed times 0.3 cubed over 3 factorial. And when I type this all into our calculator, we should get 0.009. Okay, so when we look at our term right here, this tells us, okay, if we have an alternating series, we can just take the third term in our estimation, all right? Because look at, we did all this work like we did in the previous problem. We ended up with 0.009, but let's go back to what they gave us for a moment. We got the first term is 0.3, the second term is negative 0.045, and the third term, this is the number that we got, okay? So I'm going to go ahead and highlight this third term right here. So if I'm using two terms to approximate in an alternating series, then the error is just going to be the next term or the third term, okay? So in other words, if I wanted to use 4 terms to approximate, right, that would be 1, 2, 3, 4, and it's alternating and the numbers are getting smaller and smaller and smaller, then my error will be 0.000486. Okay. Or if I wanted to use 5 terms in this alternating series, then my error would be the 1, 2, 3, 4, 5, 6th term. Okay. So this is a nice handy trick. I wanted us to kind of go through it the long way again, but ultimately show us that the answer was actually there the whole time, okay? All right, let's do one more equation kind of like this one. So it's example 3 says use the Taylor series at 0 for f of x equals e to the negative x to approximate e to the negative 0.3 with an error of no more than 0.0005. Okay, so here's what we're going to do. We're going to go back, find our table number 1, and f of x equals e to the negative x. And when we write out this series, we'll get 1 minus x plus 1 over 2 factorial x squared minus 1 over 3 factorial x to the third. Let's do one more. Plus 1 over 4 factorial x to the fourth minus, and we keep going until we get negative 1 to the n over n factorial x to the n, right? That would be like the whole series. But what this question is asking is like, how many of these terms do we have to include? Like, can I just use 2 terms? Do I have to use 4 terms? Do I have to use 8 terms? Like, how many terms do I need to use? Because we don't want to do more work than we need to get an error of less than 0.0005. Okay, so here's how we use that special rule for alternating series here. I'm going to say f of 0.3, which equals e to the negative 0.3. And I'm going to plug in a 0.3 everywhere I see an x. So 1 minus 0.3 plus 1 over 2 factorial times 0.3 squared minus 1 over 3 factorial times 0.3 to the third plus 1 over 4 factorial times 0.3 to the fourth minus, and I could keep going, okay? But I don't want to write more than I have to, so let's see what we get. We're going to use our calculator to figure out each of these terms, and we get 1 minus 0.3 plus 0.045 minus 0.0045 plus 0.000337.5. Okay, I know after that there's going to be a minus, and I could just keep going. What's really important though is you do one term at a time to put into your calculator. Like, don't do them all, because what we want to see is each individual term and how that's impacting our estimation. Okay, so we look at all these terms, and what we want to look for is this. I don't want an error of more than 0.005. So I need to find the first term that is less, or that is less than that, okay? So I go, 1 is too big, 0.3 is too big, 0.045 is too big, 0.0045 is still too big, but this term, this is the first term that is smaller than 0.0005, okay? So this is, let's make a note for ourselves. This is the first term less than our maximum allowable error. Okay, so if you don't want an error of more than 0.0005, this is the first term that's less than that. Okay, what that means is to get your estimation, you just add up the first 4 terms. Okay, so this will be our estimation, and that means, let's see, it's 1 minus 0.3 plus 0.045 minus 0.0045. When I type that all into the calculator, I get an estimate of 0.7405. And what this is saying is that 0.7405 is an estimate for e to the negative 0.3, and it's going to be accurate to 0.0005, or even more accurate. Okay, so we can sort of say, if we want to have this accuracy, this is how many we have to go to. We don't want to just keep going forever and ever. We want to cut it off with exactly how many we need to get to error. Okay. Come on back to the video in which we'll take a look at approximating definite integrals, kind of using the same idea.